Good day and welcome back to part 2 of our discussion on the chain rule. And let's just begin with a quick reminder. The chain rule is a rule of differentiation that allows us to hopefully quickly and efficiently differentiate a composition of functions. In words, the chain rule tells us the derivative of f of g of x is the derivative of the outside function, f prime, evaluated at the inside function g of x, multiplied by the derivative of the inside function. So quite a bit of pattern recognition going on. So let's go ahead and apply this to an additional example and then make an observation. If I wanted to differentiate the function x squared plus 1 quantity cubed, do I need to use the chain rule? And the answer is no. If I really wanted to, which I don't, I could expand this cube all the way out so that it's a polynomial and then just differentiate it term by term. But it is, of course, much more efficient to just go ahead and apply the chain rule. And for one last time, I'm going to go ahead and include a couple extra steps breaking this down further, and then we'll slowly but surely work our way away from doing that. So note, this is really a composition. I could think of this as being big F of g of x, since I've already used a little f, with the inside function typically being maybe the easiest thing to identify. Here it's x squared plus 1. So the inside function is x squared plus 1, and then the outside function is kind of just whatever we are doing to the inside function. And that inside function is being cubed. So the derivative of the outside function would be 3x squared, and the derivative of the outside function is simply 2x. And the chain rule tells us if we wanted to differentiate this function, little f, it would be the derivative of the outside evaluated at the inside multiplied by the derivative of the inside. So we need to take g of x, x squared plus 1, and substitute that in to our function f prime. That is, we would have 3 times the quantity x squared plus 1, quantity squared, multiplied by 2x. And let me just make a quick observation. In our previous discussions, I put a large emphasis on the fact that you could not differentiate this with the power rule. Note the reason you cannot is if you were to just apply the power rule, you'd be missing that derivative of the inside function that comes from using the chain rule. But a version of the chain rule, something we might call the general power rule, is as follows. It tells us if we want to differentiate a function raised to a power, and we apply the chain rule. We differentiate that outside function so the n comes down front and the new power is 1 less. We evaluate it at the inside function, g of x, and we multiply it by the derivative of the inside function. And note, if you compare, that is precisely what we have done in the above example. And to be honest, I usually hesitate to write down this general power rule because it's just a particular application of the chain rule. But it is a nice thing to think about in terms of just purely pattern recognition. So with that in mind, we are in a perfect position to practice some differentiation with the chain rule. So what I would like you all to do for the following 2 examples is to pause the video, maybe take 5 or so minutes, whatever it takes, and differentiate these 2 functions. So hopefully at this point you have paused the video and you've calculated a few derivatives. Let's go through the details together. And as I claimed, I'm not going to break each function down in terms of an inside and an outside. I'm simply going to talk our way through it. So in this case, we have cosine x plus 2x squared, all raised to the 100th power. And this matches up very nicely with that previous formula, the general power rule. the n value is 100. So we think we differentiate the outside function, the 100 comes down, and our new power is 1 less than 100, so 99. And then by the chain rule, we substitute in the inside function, cosine x plus 2x squared, and we multiply by the derivative of that inside function. And you are more than welcome to directly calculate that derivative. I prefer when there's more going on to include this extra step because it's just showing me very clearly what derivative I'm calculating, and hopefully it will prevent me from making a smaller, possibly silly mistake. So cutting and pasting down, we have 100 times the quantity cosine x plus 2x squared raised to the 99th power. And then we are multiplying it by the derivative above. Term by term, the derivative of cosine is minus sine. Remember, you get the negative when you differentiate the co-trig functions. Plus by the power rule, 4x. And leaving it exactly in this form is ideal. Moving on to the second example, we really do have kind of two choices here. One choice is you could leave it written exactly as it is and apply the quotient rule, or you could bring this power we have in the bottom to the top and apply the product rule. And I'm going to go ahead just for fun and rewrite it so that we can use the product rule, as I don't recall having done that in the past. Let me go ahead and note, in this case, if you have the nth root of some quantity, that's f of x raised to the 1 over n power. So in our case, the function g of x is really x divided by x squared plus x plus 1, all raised to the 1/3 power. And also, let me recall that if you have something like 1 over a quantity, and let's just call it f of x for fun, to a power, this is really the same thing as that function raised to the minus power. So it would also be equivalent to write this as x times x squared plus x plus 1 raised to the minus 1/3 power. And no, you don't have to write it this way. This is just an approach, one of many, that could work. So now when I go ahead and differentiate it and I use the product rule, and I'm going to go ahead and actually write the product rule out, even though you don't have to, just to make sure we're all on the same page. So we take the derivative of the first function times the second function plus the first function times the derivative of the second. And it's when we differentiate this second function that the chain rule comes into play. The derivative of x itself is 1. And when we differentiate that remaining function, note it's a function, x squared plus x plus 1, kind of on the inside, and it's raised to that minus 1/3 power. So we think we differentiate the outside function, so think the minus 1/3 comes down front. The new power is 1 less. We substitute in the inside function, and then we multiply by its derivative. And putting this all together now, we have 1 over x squared plus x plus 1 to the 1/3, just rewriting it so there's not a negative exponent, but a negative exponent's just fine. And then pulling that negative out, we could say minus x over 3 times x squared plus x plus 1, now it's to the minus 4/3 power, times that remaining derivative. And term by term, that would be 2x plus 1 plus 0. And we could keep going and rewriting this algebraically, combining together into a single fraction, but leaving it at this point is more than okay with me. So that completes the discussion for this current video, and I would like to highly encourage you to go to suggested problems in the book and practice using the chain rule. When we get to the next chapter and we're investigating applications of the derivative, differentiation becomes a smaller part of a larger problem, and it's something we want to be able to do quick and efficiently. So stay tuned and take care.